So we have completed our discussion on numerical techniques related to steady state problems. Okay, I just took an example of a 2D steady state case, but you can at least know that even if it is a 3-dimensional body, how can you apply the energy balance method on a certain cell, and how can you come up with the equation? Okay, and those equations are numerical equations. And I told you in the last lecture that why we call those equations as the numerical one, because you don't have analytical form of the solution, so that is why we go for the numerical solution. These are approximations, right? Now we would extend that discussion to unsteady problems. Okay, so let's talk about those unsteady problems. Sorry. So this is about unsteady heat transfer, and you know that if I just ask what would be 1D equation in this case, so you all know that it should be 1 over alpha partial T by partial T equals what? Right? You know that. If we all ask about 2D equation, that would be 1 over alpha partial T by partial T equals partial square T by partial x square plus partial square T by partial y square, and similarly for the third dimension you can write partial square T by partial z square. Okay. Now this is physically, what does it represent? Storage, right? Physically it represents energy storage. And what is that alpha? You remember that? Diffusion what? Diffusion constant. Okay, diffusion coefficient or diffusion constant. So that is something what was, KCP over what? K over rho Cp. Yes, it was, I'm sorry, this was K over rho Cp. So this was diffusion coefficient. Now the problem is to numerically approximate this thing. Okay. Now I would discuss two ways to do that one. First one, I would write down the equation straight away from finite difference. I told you what was that finite difference equation last time. Okay, once you use the Taylor series and you wrote down all the expressions for partial T by partial x, okay, you come up with something Ti plus 1j minus Tij divided by delta x. So that is something which is finite difference. Now if I write down finite difference equation for this term, 1 over alpha partial T by partial T, now be very careful, and then partial square T by partial x square. Now this 1 over alpha is a constant, that would come as it is. And here we have partial T by partial T, it means I am taking derivative of temperature with respect to time. By looking at the previous pattern, you can put delta T in the denominator, isn't it? Yes. In the denominator you have delta x last time, so this is delta T. And then what you can have is, I say that this is I is the x index. I repeat, I take I as x index. I'm sorry. So I take I as x index. Okay, and I just use n as t index. You remember I used j as y index last time. Okay, so just to differentiate between those indices, I would use this n for time index, and I would put it in the superscript. Right? So this is TIN. TIN means T at ith node, because this is 1D, right? So if I give you an example of a rod, let's say this is a rod, you say that this end is at temperature T1, this end is at temperature T2, and T1 is greater than T2, so obviously heat would start flowing from here to here. Okay, and there are, let's say, I divide those that complete length into 5 nodes. These 2 are the boundaries, and these 3 are the unknown nodes. Okay. Now see, if I say this node is I, so this node would be, and this node would be I minus 1, right? And this is the picture of this rod at time equals, let's say time equals 1 second, for example. Time equals 1 second. So if I move in time, it means I am taking more and more pictures, isn't it? I would take another picture at the next time level. Let's say at the next time level, I would have this T2, this T1, and there are the same nodes, but now they would have some different temperature. Why? Because the system is evolving with respect to time. Okay, so this may be at T equals 2 seconds. If this is the second picture and this is the first picture, what would be delta T? Delta T equals 1 second. Okay, so similarly, just look at that. I say that this picture is at n plus 1 time level, and this picture is at nth time level. Okay, you see, I am taking derivative with respect to time. So which index should be changing? Time index. Okay, time index should be changing. So I would approximate this derivative partial t by partial t as ti n plus 1 minus ti n. You understand that? If we take the derivative with respect to x, what was the index which was changing in that term? I. If we take the derivative with respect to y, what was the index which was changing in that term? J. So now we are taking derivative with respect to time. Okay, so which index should be changed? N. Okay, so this is n plus 1, it means the next time level minus the previous time level. Right? So these kind of schemes are known as, I would not go into the detail of these techniques, but just to give you some idea about the finite difference, this thing is known as forward difference scheme. No, this scheme, it means the second level minus the first level, the next level minus the previous level. For example, if I write down ti plus 1 minus ti divided by delta x, so still it is forward difference. Still it is forward difference. Okay, so you can say that forward difference in time, I would say I am approximating this term numerically by which technique? Forward difference in time. Okay. Now I need to settle the second term. Let me write it down on the next slide. So this was 1 over alpha ti plus 1 ti n plus 1. You see, I would not change the other terms, and then this is ti n over delta t. Yes, and then we have partial squared t over partial x square. Okay, again all of the expressions which I would write down over there, these are coming from Taylor series. You do some kind of simplifications, modifications, and you come up with those terms. But anyways, for second order ordinary differential term, for second order term, now what do I mean by second order term? I am talking about partial square t by partial x square. So I would approximate this term like ti plus 1 n. I am not changing the time index now, I would be changing I index. So ti plus 1 n minus 2 ti n plus ti minus 1 n over del x square. And this finite difference approximation or the numerical approximation is known as central difference scheme. Okay, you see that you are talking about temperature of ith node, isn't it? That's what you want to find out. But this is in the center of I minus 1 and I plus 1. You are using information of those two nodes, those surrounding nodes. So that is why it is, you can say this is a central difference scheme. I repeat, this is I minus 1, this is I plus 1. You are interested in the value at I. This is I plus 1, this is I minus 1, excuse me, and you have I in the middle, right? So that is why it is kind of central difference scheme. So I would use this term over there. So this is ti plus 1n. Sorry? What kind of first derivative? Yes, that you can do. That's another way of describing it. That's given in your book. You can see that. Okay. So now just look at one very clear thing. On the left hand side, what is the index which is changing? N. Why? Because it is time derivative, so n index was changing. On the right hand side, it was derivative with respect to x. So what index is changing? I index is changing. Okay, so now I can just simplify this term. I would erase it. Okay, so let's say I would just find out ti at n plus 1, because that's something which I want to know. And you know that if you know the initial condition, it means you know t equals 1 information. If you know the initial condition, it means that t is equal to 0, you know the information. Okay, so you can talk about the next time level. Okay, just let me write it down in the simplified form. I would simply keep this term on the left hand side and I would keep all other terms on the right hand side. So this is alpha del x square, and delta t would also be multiplied over there, and then I would have ti plus 1n minus 2tin plus tn minus 1n. Sorry, this is I minus 1. I'm sorry for that. This is I minus 1 divided by del x square. Sorry? Okay, oh yes, that has already come out. So, and then finally I would have plus tin, right? So this is the simplified form. Now just look at that. You know, you want to find out value at the next time level, and you know all the values at the previous time level. Just look at it very carefully. This is quite interesting, that you want to find out value at n plus 1, let's say the second time level, but obviously at n time level, which is the initial condition, you already know that, isn't it? So it means all the points on the right hand side, you know their values. Why? Because they are from the previous time level. Okay, so these kind of schemes where you can find out one unknown in one equation, these schemes are known as explicit schemes. You remember I told you last time as well. These schemes are known as explicit schemes. Now just see, and I told you there is a disadvantage associated with those schemes. N is time index. Like for example, how do you see a video? Okay, how do you see a video? You have many pictures combined together, isn't it? Like for example, if I ask you to have a video of 10 seconds and I give you a set of pictures at time equals 1, time equals 2, time equals 3, time equals 4, right? So you would, like for example, if I am moving in this way, you can see me continuously. But for example, if at this time I am here, in the second picture I am here, in the next picture I am here, right? So what I am trying to do, you are looking at me by a discrete view. A discrete view, it means you know where I was at time equals 1, where I was at time equals 2, similarly at time equals 3, and you can have a set of like 10 pictures. Okay, and by combining them you can see. So I say that at time equals 1, n is 1. At time equals 2, n is 2. Okay, so that was basically the meaning of n. Now you see that all the terms on the right hand side are known to you, and there is just one term which was to be found out, and that is unknown at n plus 1 time level. So this is basically an explicit scheme. Okay, I would use okay, and there was a disadvantage. We were talking about that disadvantage. So that disadvantage was what? You remember that? Yes, the stability condition. You have to put restriction on the size of x and t. You have to put that restriction. Okay, and that restriction, this number, generally this number is known as diffusion number. If you look at the CFD books, this number is known as diffusion number. Okay, and it depends on the numerical technique. It depends upon the numerical technique what is the stability criteria. Okay, like for example, if I say that the numerical scheme which I am using here, it says its stability condition requires that alpha delta t by del x square remains to be less than equal to 1 by 2. If I say this is the stability criteria, what does that mean? That means you can have any value of delta t, you can have any value of delta x, and obviously alpha is a coefficient which is known to you. This is a material kind of property. This combination needs to be less than 1 by 2 if you want to have a stable solution. I told you what was the stable solution. Stable solution means that if I find out, let's say this is the rod, this was node 1, this was node 2, this was node 3, and this is 4. This is known temperature because these are the boundary conditions. Let's say I ask you to plot temperature at node 2 with respect to time, and I say that this is the boundary, this is the initial condition. Let's say this is the initial condition. Okay, and let's say I say that if I just plot all the values with respect to time, I solve this equation and I plot it with respect to time, you say that this solution converges to a steady state. Let's say this is the steady state. What do you mean by steady state? No change with respect to time anymore. Okay, so this is the steady state solution. So this is stable solution. Now if you take higher delta t, let's say your delta t is, let's say 1 second, and your delta x is, let's say 2 seconds, no problem at all. Still your solution may be stable. If you keep alpha equals 1, your solution may be stable. But the problem would be with the accuracy. Remember that stability is something else, accuracy is something else. So to be more accurate, you need to keep delta t and delta x within, again you need to keep those two variables very small so that you have more accurate solution. So accuracy is something else, stability is something else. So for example, if you talk about the unstable solution would be if you start from this point, so its amplitude would diverge and finally it would go to infinity. And if you are solving it in a MATLAB, you would have like 10 raised to power 19 or 10 raised to power 7 or 10 raised to power 8, something like that. Okay, so that's what you mean by unstable solution. Just hold on, one by one. Okay, repeat your question. Okay. You are talking about T2? It just needs to be settled down. It needs to be settled down after, let's say, some time. It needs to be settled down at a value. If it is not settling down and it is basically going like this, so that is something which is unstable. Okay, if it basically stays here just like that, and by the way, there is something known as, you might have heard about this word, boundedness. if the solution is bounded means it remains within certain limits. You see, this is not bounded. This is basically expanding. So this stability is kind of boundedness. You can say solution needs to be bounded. So that's what stability describes. If your solution is unbounded, it means it would go to infinity. After some time, you would have like infinity values, 10 raised to the power 19, 20, whatever. Okay. So this is about stability condition. So I hope you understand what is the stability condition. Right. So for this particular scheme, stability condition is given in your book. You can see that. Okay. So this is the introduction about the numerical technique for unsteady problems. I would start from this point onwards. We would move on to 2D problems, and I would solve one example as well. Okay, tomorrow. Thank you.